A very good afternoon, everyone, and welcome to third day of Deep Learning Summer School by IIITDMJ Jabalpur. My name is Sunaina Singh, and I would be the chair for this session. I hope you all are well rested after yesterday's long back-to-back sessions. This would be a practical session and would be taken by Mr. Samir Jain. Mr. Samir Jain completed his PhD in CSE from IIITDMJ Jabalpur in 2024 with a focus on AI for medical imaging. His expertise lies in deep learning, image processing, machine learning, and blockchain technology. He is currently working with alphaTKG Private Limited on AI projects, and also has served as a guest faculty at IIITDM Jabalpur only. And during his PhD, he also contributed to courses on deep learning and blockchain under Professor Aparajita Ojha as well. Thank you, sir, for joining us today. And we now request you to kindly take over and begin the practical session. Thank you very much.
Okay, thanks, Sunana. So for this brief introduction. I welcome you all again in this session. This is third session. We will be discussing about how we can create a neural network, or we can say that how we can create MLP, multi-layer perceptron. So today we are going to discuss using Python, we can create MLP without any library like Keras or PyTorch. So we will be using plain Python programming language. We will be using certain small libraries that are available with Python, and then we will build a network. So without wasting much time, uh, I will share my screen first. Yeah. Okay. So first thing is that I need to check with you all if you are able to write something in the chat. Uh, yeah. So you can write hi in the chat so that I'll be able to connect with you all. Yeah, great. Great, great. Okay. So let's discuss something uh, what we are going to do today, and then we will start coding on that. So this is the interface that you can see in my screen is a Google Collaboratory. So Google Colab. So Google Collaboratory is something, a programming interface or cloud-based platform that is given by Google. So there we get Google, the notebooks, Jupyter notebooks that we get, and then we can do certain kind of codings on this Collaboratory. There are certain languages like R programming language, Python. There are certain packages like deep learning packages like PyTorch is there, Keras is there. So whatever you need is there inside this collaboratory. So I have written codes in this Google Collaboratory, and again I will be writing codes in Collaboratory only, so that nobody needs to like install anything in their standalone systems. They need to just open this browser and then start coding. So yeah, so let us discuss what we are going to do today. So first thing is that first we are going to make a neural network. So simple feed forward neural network, that is multi-layer perceptron, we are going to make today. So it is a fully functional style. Functional style means all of the codes are written in the form of functions. So Python functions. We will be using Iris dataset. So Iris dataset is a 3-class dataset. So here you can see that Iris is a flower. So this flower has three types of species. So one is Setosa, versicolor, and the third one is Vaginica. So all these three species, they get differ in the when we will talk about sepal length and width and petal length and width. So based on these values of sepal length and sepal width, petal length and petal width, we can identify which flower is this. So is this Virginica, or this is this versicolor or setosa? So this dataset comes readily with the Python when you'll install it. So There is sklearn package. So inside sklearn, there are certain data sets, amongst which I will be taking this data set, that is iris data set. Okay. Now we will be making some multi-layer perceptron. Before that, uh, what we can do is we have to download the data set, then we have to convert the data set, and then we have to make it compatible with the model itself. Then there are certain activation functions that we will be using, and based on those activation functions, we will test how is the output. Okay. Now, there are certain uh, activation functions, more activation functions like softmax activation is there, that we will be using because it is a more than one class problem. Like it is not binary, it is categorical problem. So we will be using softmax and all that. Cross entropy loss we will be using. We will be finding accuracy score. Then we will train the model based on, as you have learned in theory sessions, like how there is a weight matrix, there is activation function. Then we will take the derivative using backward propagation, and then we will plot these graphs. Okay. So first of all, just tell me that how many have you ever opened this collaboratory? Yes or no? Have you ever used collaboratory, Google Collaboratory? Yes. Okay. Okay. So many of you are known with this collaboratory. So I will tell you all how you can open your collaboratory if you haven't opened it earlier. So I'm writing, you can write Google Colab first. So welcome to Google Colab. Okay. Here. So you can open Google Colab. Yeah. So this page will open. Now what you have to do is, I think because I'm using a browser where I'm already signed in. So if you are not signed in, it may ask you to sign in. So you can sign in with your Gmail ID, and this screen will come, and then here there is one option that is new notebook. So I'm clicking on new notebook. So I think you are with me, you all are with me. So you can type in the chat if you are in the new notebook. So you can write NB in the chat. We'll come to know that, yeah. So you are in the new notebook. Great, great. Okay. So let us start building our first multi-layer perceptron without any library. I mean to say that I mean to say that we are neither using PyTorch nor we are using Keras, okay, or TensorFlow. So using plain Python programming, we will be doing this. So first package that we are going to import is import NumPy as NP. So NumPy is a library, a small library, mathematical library where you can create arrays and then you can do certain operations on those arrays. Okay. So this is NumPy. Second is import matplotlib dot pyplot as plt from sklearn.datasets. So I was talking about this sklearn. So sklearn is a library where there are certain things like there are certain this machine learning engines are available where you can get certain data sets. So there are certain codes that are predefined, they're ready to use, and then you can import those sklearn libraries and then you can directly do that. But in this case, in today's session, we are using sklearn data sets only. So we are, yes, so it is saying from sklearn.datasets import load iris. Yes, correct. So I don't need right now. So I am deleting it. So now second thing is from sklearn.model selection. Yes. So we need sklearn.model selection, test train and split, and then we have to import. Oh, I don't need this. So I need even I need from sklearn dot preprocessing. I need standard scaler and what else? Standard scaler and one hot encoder, I think. Yes, one hot encoder. Yeah. So these are the things that I will be needing, and they are required for our program to give the desired outputs. Okay. So here you can see that if I'm running this cell, so there are two ways to run this cell. Either you can use shift plus enter, or you what you can do is you can use this play button. So it will work. So I think most of you have imported, so you can write imported in the chat. Imported. Imported. Okay, I'll explain everything whenever it is required. So don't worry about that. Why a standard scalar, one hot encoder? What are these? These are only when I will use this, because I have just imported it right now. I have not used these libraries, so I when I will use it, I will tell you what are these. Okay. So first thing is that we need to load the data set, iris data set that we will be using. So we will write iris equal to load iris. Yes. So iris is the data set that we are going to use today. Now let us check what is iris. Okay. So iris has two things. One is iris dot data. So iris has data, iris dot data. Iris dot data means when we talk about a data set, suppose let me open Excel. Okay. So suppose we are talking about iris data set. Okay. So we are talking about petal length. Then we are having petal width, sepal length, and sepal width. So and then sepal length and sepal width. Okay. So this is suppose it is in the form of centimeters. So suppose it is 10, then it is 20, it is 25, it is what 34. Okay. So suppose this is the data set. I'm copying this. Suppose this is the data set. Hmm, okay. So I'm copying this and I'm populating. So suppose this is the data set where we are having some instances. This is input and we need some output. Output should be in the form of which flashes. I'm making it 23, I'm making it 45, I'm making it 19, like suppose it is 78, it is 24. So suppose these are different data sets, and now output is, so suppose this is Virginica, this is what else are these species? So suppose this is Virginica, this is Setosa, this is again Virginica, and the other one is a versicolor. So versicolor. So this is versicolor, and this is again Setosa. Okay. So this is the complete data set. So this data set has two parts. One is data. So we will call this as data, and the other one is target. Target means what is the output, or what is the actual label of this data, what is this data is known as. So this data is for Virginica. Okay, so the target is Virginica. For this data, the target is Setosa. So in this way, yes, Iris is the name of dataset. Yes, it is name of dataset. Okay, so please focus on this thing. Don't focus you have much time for coding, so please focus what I'm saying on about this. So this is data and this is target. Same way, when we have taken load Iris, like we have loaded Iris dataset here. So iris.data will give us the dataset. Now suppose if the data is of 150, suppose there are 150 rows. So I am writing if there are 150 rows and there are 4 features. So what is the dimension of this array? If if I'm talking about, suppose there are how many rows? 150 rows are there. Okay. So 150 cross 4. Yes, correct. Gaurav says that it is 150 cross 4. So 150 cross 4 means there are 150 rows and each row has how many columns? 4 columns. So these 4 columns for any row will represent feature. So it is known as feature. So this is the feature vector for this Virginica. This is feature vector for Setosa. This is feature vector for Virginica. Then whatever this is, and then this is for Setosa. So this is versicolor. So these are the features for any flower. These feature will define whether it is Virginica, Setosa or versicolor. Okay. So in this way, when I will iris data, I will store this in a variable known as x. So x equals to iris.data. When I will write x.shape, it means what is the shape of that matrix. So the shape of that matrix is 150 cross 4. So in this way, now let me now tell me, suppose I am writing y equals to iris dot target, iris dot target. Now tell me what is the what should be the dimension of this particular y matrix. So when you will see that this is the matrix. So what should be the dimension? 150 cross 1. Okay. So let us see y dot shape. So cross 1 it will not say, but it will say there are 150 rows. Okay, so it is same like 150 cross 1. Yeah, correct. So most of you, like every one of you who had given me answers, I'm very happy with you all. Like you are very prompt in response. So it is 150 cross 1. Okay. Now we will reshape it correctly. Why reshaping is needed? So instead of 150 cross 1, we need it in reverse shape. So I will do it like this: dot target dot reshape -1, comma 1. So it will convert rows into columns. So what is this? Now it is y dot shape is 150 cross 1. Whatever we need it over here, it will convert it likewise. Okay. So I will write. Uh, I think you must have got what I'm saying. So we have got the data set in this form, this and this. So yeah. Okay. So -1 means is converting dimensions x to y, y to x. We can do transpose also. Yes, correct. Jui. Now, now we will move further. So we have to do a lot of coding. So instead of discussing about these small things, we will focus on more on the major part of this particular session. So first is that now we need what happens is, suppose Virginica is we will make this as class 0, then versicolor is class 1, and setosa is class 2. Okay, so we will make a one hot encoding. One hot encoding means there are three classes, so there will be 3 bits. 3 bits. You'll call it as 3 bits, okay, or three integers, okay. So since Virginica is 0, so we will call it as 001. Okay. Then it is 1, so we will call it as 010. And it is 1, so 100. So this is known as one hot encoding. One hot encoding means the classes, whatever classes are there. So suppose this is this is encoded like this. So it is Virginica, then the last bit will be 1 for Virginica. Then if it is this versicolor, then middle bit will be 1, and if it is setosa, then the first bit will be 1. Okay, so it will show you, like, if it is setosa, then the first value will be 1, other will be 0. So this is known as one hot encoding. One hot encoding, OHE. Yes, so this is one hot encoding. So we will convert this in a one hot encoder, because we are making, I will tell you why we are doing this one hot encoding later on when we will create neural network. Okay. So I will create an instance of this encoder. So encoder equals to, now we have taken one hot encoder here. So one hot encoder, this. So I will write encoder equals to one hot encoder, one hot encoder. Okay. And here we will write sparse output equals to false. Sparse output, because one hot encoding is something where there are majority of zeros. Here there is majority of zeros. So what happens, you must you can read at your home what is a sparse matrix. Sparse matrix. So when you will read data structures, so you will come to know what is a sparse matrix. Sparse matrix. Okay, sparse matrix is something where there are more number of zeros. So instead of making an n cross n matrix where the complexity is O of n square, we will come make it in a linear complexity. So instead of exponential, we'll do sparse encoding. So sparse output equals to false. Now we will convert this y to the encoding. So we will write y underscore encoded equals to encoder dot fit transform. Fit transform, what it will do is, this encoder, that is one hot encoder, will fit on this data and will convert this data in a new form. That is, so when I will write y underscore encoded, so you will check, you can check that this is in the form of like one hot encoding. Okay. Earlier, when you will compare this with y, so y is something 12012. Okay. So here we are having this kind of encoding. Okay. We can also use np dot unique y. So unique values. So there are unique values, 0, 1, 2 are the unique values. And here there can be only two unique values, 0 and 1. But the position matters over here. Okay, not the value, but the position. Now we will proceed further. So here we have converted it to encoding. Now there comes the part of converting the inputs. So what happens is when we are training a neural network, we need to convert the input also into a certain domain where the data is normalized actually. So while when we will normalize the data, because sometimes suppose I am talking about petal length. Suppose the data is something where petal length is in the form of floating point values. Sepal length is in the form of integer values. So it to train the neural network with different domains of values, it will not give good results. So instead, what we do is we convert this into a standard normal distribution. So standard normal distribution means standard distribution or normal distribution. It means that there will be a mean of zero and uh, a deviation of one. Okay, so in that way. So let us go back. So here we'll make again scalar. So scalar equals to standard standard that we have taken. Yeah, standard scalar. Yeah, correct. So Google suggests me. So scalar is equals to standard scalar and x scaled equals to scalar dot fit transform x. So earlier when we will talk about x, so if x is like this, 5.8, 2.64 and 1.2. So x scaled, this will be like this. Okay. So this is how we have converted the data. So we have now, earlier we were having x and y. Now we are having x scaled and y scaled. So what is that y? That is y scaled or something. Y encoded. So x scaled and y encoded. There are two variables now. So our data set is converted into x scaled and y encoded. Now, now, as you might be knowing that we have to split the data set. Do you know? Anybody knows uh, data set splitting? Yes, correct. So we will be, Gaurav is correct, very right. So we will be splitting this data set into training and testing. Yeah. So splitting generally we do in 80 is to 20, like 80% of data we will be using for training the neural network and 20% we will be using for testing. So this is 80 cross 80-20 rule. Okay. So let us start with splitting the data set. So we will be using a library. So x underscore train, comma x underscore test, y underscore train, comma y underscore test equals to train test split. Yes. So it we will use this function train test split. It is already there. So I will clear hide outputs. So I will hide these outputs. Okay. So we have taken test train split. So we are using this test train split and it is okay. Scalar code is this. I'll copy. I'll keep on copying this thing. After scalar code, I will keep on copying. So what I have done, I have this or splitted this data set that has x scaled and y encoded into x train, x test, y train, and y test. Okay. Oh, sorry. I have to give it to everyone. Actually, I have sent it to Gaurav. Yeah. Okay. Now, I will ask everyone what is random. Okay, random state is something. Random number generator is there. Random number generator, what it does, it takes one seed value and then using that seed, it generates random numbers and using those random numbers as the row number. in the data set, it will take out those rows. So those 80% of rows it will take out, and remaining rows will be considered as test. Okay. So random state is like that only. So this is the seed, actually seed. 42 is the seed through which we are generating random numbers. Now, we will come back. I'll ask everyone to open Alex Lee Nail. Alex Lee Nail. This nn.svg. Yeah. So today I'm telling you that we'll make a neural network. So this is this through this web page. I'll copy this and send it to you all. So this web page, we can just see that what we are, how, what kind of network we are doing right now. We are uh, creating. So I will make it 0, 0. Okay. Now, now just tell me that the what is the size of input. If suppose I'm taking single input like this is single input. So what is the size of input? So how many values are there? Four values are there. Juhi says four. What about others? Four. Yes. Javed says four. Yeah, great. Nirvani says Renji, Yamini. Yeah, correct. Diksha, correct. Correct. So there are four inputs. So what we will do, we will take four neurons in the input. So there are four neurons. Got this thing? We can take another seed value, Sangeeta. So I'm you people I'm talking about because we have only 2 hours to spend in this coding session. So please, whatever I'm telling you, if it is necessary, I'll keep on discussing about. If it is not necessary, you can do it by yourself. Like, so random number is there. You just go through it. What is random number generator? Okay. Yeah. You can take another seed value. Don't worry. You can take anything. So here we have four inputs. Now there is one hidden layer. Okay. Now there is one hidden layer. So I am taking hidden layer with 8 neurons. With 8 neurons. So every neuron will be connected to other 8 neurons. Okay. So first one will be connected with this neurons. So suppose these are weights. Four inputs are only there. I have told you earlier, Pooja. Four inputs are only there. I have told you in the X vector that there are only four inputs. 4 cross n number of rows. So there are only four inputs for each sample. For each sample. Okay, so this is one sample. So how many inputs? Four inputs. Okay, in this tool. So in this tool, I have to write four over here. Four. No, there is no rule, Juhi, to take how many hidden layer neurons. There's no thumb rule. Okay. Now tell me how many classes are there? How many classes are there? Anybody who can tell me? Yeah, Nirvani says three. Oh, so much answers are there. So many answers. So there are three outputs. Okay. So there will be three neurons. So in this way, you will create a MLP, multi-layer perceptron model. So here there'll be a weight matrix. So there are how many weight matrix will be there? Can anybody tell me? How many weight matrix will be there? Weight matrix. So there will be two weight matrix. One will be input layer and hidden layer. Between input layer and hidden layer. So weight matrix is something. So when you will see a connection, over here, this connection is actually a weight, a value, some value. So we will call it as a weight matrix because we will multiply that with some value. Okay. 8 hidden layers is actually hidden layers will help in getting more, like if the process is complex, like problem is very complex to find, like input is very complex. So hidden layers help in solving those. More hidden layers will be there, more complex problem we will solve. You can read about XOR kind of a thing when you will read perceptron model. So you have to read about those things. Okay. So here, the weight matrix, one weight matrix will be between input and hidden layer. Second weight matrix will be hidden and between hidden and output layer. Okay. So there is no thumb rule. Okay. Please listen whatever I am telling you. Please listen carefully. There is no thumb rule for weight. This hidden number of hidden layer neurons. Second thing is yeah, XOR problem. So XOR problem held in increasing the by increasing the neurons hidden layer, you were able to solve XOR problem. Okay. Now let us come back. So where were we? Yeah, in this. Now, so we are now going to create our model. Okay. So what is input shape? What is input size? Can anybody tell me what is input size? So we will write is at x dot shape 0. X dot shape 0. Yes, it is 4. So x dot shape, we will write it like this. If x dot shape is this, oh, sorry. X dot shape is this, then the 0 means this is 0 and this is 1. Sorry, I have to write it 1. So x dot shape 1. So x dot shape 1 will be 4. Because this is 0, this is 1. Suppose I am storing it into some other variable b equal to x dot shape. So b0 will be 150. B0 will be 150 and B1 will be 4. In this way, we will write x dot shape 1. Now, what is the hidden size? So hidden size has no thumb rule. So we can write it by ourselves. So hidden size will be 8 neurons. Okay. Output size. Output size. Output size, we already know that it is 3 class problem. Okay. So this is 3. And now we have to set one thing that is known as learning rate. So learning rate is 0.1 we will set. When we are talking about deep learning problems, like if there are hundreds of hidden layers in those big neural networks, then we take learning rate very small, like 0.01, 0.0001. In my PhD, when I was doing research on like anomaly detection in wireless capsule endoscopy images. So I've seen that while we are doing segmentation, we are designing segmentation solutions, segmentation of images. So there we need to have a small learning rate, very small, 0.0001, 10 to the power minus 4. But in classification problems, sometimes -2 or -3 will work. Okay, it is now -1 right now. We have set it to -1 because it is very small problem. Only 150 samples are there, and they're very easily, you can identify that what flower is this. So it is not very complex. Okay. Now epochs. So epochs will take like 1,000 epochs. Very small. It will take like hardly 15 seconds to train the network. Okay. Now this we have done. So I will copy this and paste it over here. Okay. Now, so what we have done till now? So we have taken iris data set. Then we have converted the data and target to standard scalar and one hot encoder. Then we have splitted this data set, and then we have initialized some variables like input size, hidden size, output size, learning rate, and epochs. Epochs, I will tell you later on what is epoch. Okay. Yeah, we can give it directly. Okay. Now we are writing. So in this session, actually, I was focusing on to tell you that there are certain activation functions. Can anybody tell me what kind of activation functions you have seen earlier? You have read about, like, what kind of activation functions? Sigmoid, very good. Softmax is ReLU 10H. Okay, good. Good. Leaky ReLU. Okay, great. This answer I got. Karthik says sigmoid, 10H, ReLU, and leaky ReLU. Great. So we will be taking these four activation functions, okay, today. So Karthik, I will be taking these four activation functions. So I'm writing def get activation, because I have told you that we will not be using any library. So we will design our own activation functions because we know now the formula of all the activation functions. So get activation functions, and then we will give the name. Okay. So there is lambda function. Lambda function. I'm not talking about activation function right now. I'm talking about something that is lambda function. So lambda is we are creating a generic function, or we are taking no name. Like there's no name for that function. So we will use lambda for that, and then we will be calling, yeah, anonymous function, no name. Okay. So I'm writing, and then you will be able to find it out. So if name double equals to, first is we will take sigmoid. So sigmoid activation. So what we will do is we will take act. So activation function is act is equals to lambda 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 function. So lambda x. So lambda is a function that will take x value, and it will return something based on that x value. So 1 upon 1 plus e to the power. So we will use np.exp, np.exponential, np.exp e to the power minus x. So this is our activation, and then we will use derivative. Now tell me why we need derivative of a function. First order derivative we'll take. For reducing error, yes. Gradient, yes, correct. So I was expecting something other, like back propagation or something. So we need gradient to back propagate. Like, yes, so derivative is needed for back propagation. Yes. So we will take derivative of this function. So derivative is equals to lambda x, and then we will take x into 1 minus x. So x into 1 minus x. So this is the derivative for sigmoid. Now we will take another function. So name is we'll take 10h. 10h. 10h is we already know that this is np dot 10h, and this is x. What is the derivative of 10h? Anybody knows the derivative of 10h? 1 minus x square. So this is derivative of 10h. Okay, so lambda x is to 1 minus x square. Oh, sorry, 1 minus x square is, yeah, 1 minus x square. Now, now third thing is that we will take ReLU activation function. Okay, ReLU, rectified linear unit. So ReLU is something. Anybody knows what is ReLU? ReLU activation function. So ReLU activation function is something exactly max of 0 comma x. Great. So lambda x. So we will write like that. Lambda x, lambda x is to np dot maximum 0 comma x. And now derivative. Derivative will be either 0 or 1. Okay, but so so lambda x, here we will use np dot where. So np dot where is something. Suppose I have a matrix like this, 1 comma 2 comma 3 comma 4. Okay, so I have an array. I have an array like this. So in this array, suppose I want to write like this: the values that are greater than 2, the values, oh, please don't write, focus over my whatever I'm explaining right now. So yes, so here please see what I'm asking. Suppose this is an array, Python array, where there are 4 values. I need that whatever values are greater than 1 should be 1, and whatever values are less than 1 should be 0. So what we will do is, we will do one thing. We will write np. We will use np. So I will write numpy np dot where, np dot where. Now what is the condition? Condition is that any value in this array. So this is x array. This is x array. So any value in this x is greater than 1 should be 1, else 0. So np dot where x is greater than 1. So what are greater than 1? 2, 3 and 4. So these values will be 1, and the values that are less than or equal to 1 will be zeros. So what will be the output of this? Applying this np dot where, what should be the output? 0 triple 1. Correct. Correct. Shruti Pragyan. Yes, correct. 0 triple 1. That is what we are doing right now over here. So np dot where we are finding the derivative. So x is greater than 0 should be 1, else it should be 0. Now leaky ReLU. Leaky ReLU, okay, I'll do that. Leaky ReLU needs some alpha factor. So if, and this is last activation function. So what we will do is we will do elif name equals to leaky ReLU. This is the alpha factor. Leaky ReLU is something that on the negative side, it is having some value. Leaky ReLU is like that only. So because in ReLU, whatever is less than 0 is 0, and greater than 0 will be same value x. Here we will have some alpha quantity that will be multiplied. So here alpha is taken to be 0.01. So for leaky ReLU, if activation is something lambda x np, yeah, okay, and this is np dot where x is greater than 0, yeah, 1 and 0.01, yeah, correct. Now we will use one more thing. Mhm. although if we will write LF or not, no issues, but it will make us like use only one function, and then we will take some the last one. Else is something like raise value error. So we will raise value error, that invalid function name. Okay. Now return division and derivative. So I will copy this code to everyone. Please copy it in your machine. So done till now, everybody? Half of the way we have gone. Yes or no? Done? Yeah, great. Yamini says, Nirvani says yes. Rohan is yes. I'll be waiting for others to join. Sorry, to this to write. Great, great, nice. Okay. Now we will have to focus upon other activation functions. So in this, we'll come to this thing. Okay. So in this, we will use activation functions after first layer, after second layer, but after third layer, there'll be one activation function that is a special activation function, because it has to predict, although there will be three outcomes in the form of like this three outcomes will be there. So suppose it will give you some values. Now there is a softmax function that will convert these outputs such that the weights when we will add will be one. Like probabilistic modeling. It is known as probabilistic modeling. What it will do is it will give some probabilities such that whatever comes out when we will add, it will add up to one. But whatever will be the highest will be the identified class. So suppose first neuron, this one, this neuron is having, this neuron represents setosa. This is versicolor and this is virginica. Setosa, versicolor and virginica. Let's take that setosa has probability of 0.6 and versicolor and virginica are having zero point 0.2 and zero point 0.2, like this. So I'm writing 0.2, 0.2, sorry, 0.6, comma 0.15 and 0.25. This. Okay. So this is the output. Suppose here in the first neuron, the output comes out to be 0.6, second neuron 0.15 and 0.25 is the last neuron. So which one has the highest probability? Can anybody tell me? 0.6, correct. 0.6 is the highest probability. Suppose that first neuron is for the probability, for the identification of setosa. So the highest probability, the class that gets highest probability will be the leading class, or will be identified as, the input will be identified as for that class. Okay. So in this way, we are defining, we need actually, yes, that is predicted output. And for that predicted output, we need to convert the input to that particular output using softmax. So we will be using softmax. So softmax converts it into probability. Okay. So def softmax. We will convert this to the softmax. Input will be X. Suppose it is X. X is the input. So first we will find the exponential term. Yeah, correct. And return keep them is equals to true. It is correct. Exponential x and np dot equals to np dot exponential x, and return exponential. Okay, it is not computing mean, so I will write it over here. So exp underscore x equals to np np dot exp there is one term that we will be using over here to save to for the stability, like to save the model getting too much of gradients, big gradients. Okay, so I'll tell you. So x minus np dot max, whatever in that particular row. Okay, whatever it comes. So np dot max x comma x is equals to 1 and keep dims equals to true. Yes, this one. Yes, this one. This is the softmax. So return exponential np dot sum exponential. Yeah. No, we need mean and okay. Yes. 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 Okay. So this is for like softmax. So exponential x, first we will compute exponential x because it is for all. So if we are reducing it with maximum value, then it will be 0. Okay. So whatever maximum will be 0, otherwise all things will be negative. Okay. So x minus 0 is 0, x, and then other things will be likewise smaller. Okay. Now return exponential x divided by np dot sum. So that is softmax, like the value divided by the sum of all these values. Okay. So this is softmax. I will write it. I will copy it there. Now, now for back propagation, I need to know from you that what we compute to make to back propagate. So what we compute actually. Okay, keep dimensions equal to true, like same dimensions we will have. How I can say, like we should not change. Like suppose if we are taking it row wise, so it should not collapse those rows. Okay, okay. So I was asking that. Yes, we check loss. Gaurav is correct. So every time I can see that Gaurav is giving me correct answer. So yes. So back propagation, we need to compute loss actually. So here we will take cross entropy loss. Cross entropy because it we also call it as categorical cross entropy loss. Okay, because there are more than one classes. If there is only single class, then we will call it as binary cross entropy. But if there are more than one classes, it is categorical cross entropy. Okay. So I will write def. What is that cross entropy? And then now how to find the loss? So first thing is that in this we know what is the actual label. We already know. So as you can see here that whatever is predicted will be compared with the actual label because it is supervised learning. Supervised learning means we know the target, we know the actual target, and we train the model based on those targets. So whatever model predicts and whatever we want, whatever is required. So predicted minus required is the loss, actually loss. So we do that likewise. So first thing is that so cross entropy is loss y true, whatever is correct, and y underscore pred, whatever is predicted. Between these two, we find the cross entropy loss. Now we will take the, because loss is a single term, so we will take the mean. Okay, so return np dot mean y true into np log y pred plus 1 e to the power minus 7. Yes, Here 1 e to the power minus 7 is taken because log term we are using. If y pred is 0, then log of 0 is undefined. So to save it from that log of 0, we add some term that is very small term we add to prevent this to prevent this particular term to get computed like not defined. Okay. So np dot mean, uh, but we have to do like, uh, no, this is not correct. So don't like rely on the codes that are given by Google. So what we will do, minus of np dot mean. Now we will find the max argument. So np dot arg max. Okay. Sorry, not here. Np dot sum. We will take the sum, and then we will compute the loss for each y. For each input x, we will find the loss for each output y. So np dot sum y underscore true. So y log y hat. Y hat is something that is predicted. So y true into np dot log y hat. Y hat means y predicted. So y underscore pred plus 1 e to the power minus 8. So 1 e minus 8. That we can add this term 1 e to the power minus 8. And we will do this access for each row actually. So epsilon comma, this is for, so np dot log comma, no, not here, but here. No, yeah, comma x is equals to 1, because we'll do np dot sum y true into y pred. Okay, yeah, x is equals to 1. So this is the computation. Yes, correct. And np dot mean. Okay. Yes. np dot mean, np dot sum y true into np dot log correct y underscore pred plus 1 e to the power minus comma x is equals to 1, and then this. Okay, this is correct. Define 24. What is this? Okay. So Sangeeta is asking me why we need to test what activation function will help in better training the network. So you can take only one activation function in your model. You can directly train on that, but we need to check that which activation function is there. Mean square error is sometime, Gaurav, we don't take, because mean square error we take when we are doing some regression kind of a problem. Regression means like actual value we are predicting, like in stock markets, temperature prediction. Okay, the real values prediction. Here we are doing classification. So classification we don't take MSc. Yeah, cross entropy is something like probabilistic modeling. So we will suppose there are three classes. So what is the effect of like one class over other classes? So we will take with that like highest probability of that class, and then this we take. So this is cross entropy loss. Okay, while making one that is having highest probability, and that is dominating others. So that is something like that. Okay. So this is cross entropy loss we have done. Uh, Some is for all losses. Some, Aditya, we are doing some because we have to find all the losses, and then we have to find the mean. So suppose uh, suppose the loss is here for this, the loss is 0.01. The loss comes out to be 0.02 here. Here it comes out to be 0.012. Likewise, so what we will do is we will add these two, all these. So suppose we will add these, so there will be sum, and then we will divide it with the number of these rows. So there are how many rows? 6 rows. So sum divided by 6. That we have done. So we have taken np dot mean. So we have taken mean of all these sums of all these vectors that are multiplied. X is equals to 1 means x is equal to 1 means row wise we are doing it. Because it is a 2D vector. Okay, so now we will train the for, the last thing is that we have not taken any metric. So how we are our model is performing. So we will take accuracy score. So your take home assignment will be you have to add more metrics. Like after accuracy, you can add like precision recall, F1 score, and all that. Okay. So y true and y pred is np dot mean, np dot arg max y true, x is equals to 1 equals to np dot arg max y pred. Correct. X equals to 1. Okay. Tell me. I think you all must be getting confused with x's. So you can do some exercise like you can take a 2D array. So x equals to np dot array, or you can take 2D array like this. And then 1 comma 2 comma 3 and 1 comma 2 comma 3. So x is the array, and then you can use np dot sum x comma x is equals to 1. So it is 6 comma 6. So row wise you are doing. So row wise sum you are doing. So x is equals to 1 is something row wise. Okay. So you can take this as your exercise. You can find it. I'll share the code. Don't worry. Yeah, I'll share this whole code. So now we will try to define the model. So def train model. This is very important. Now everybody please focus on. I will like to call your attention over here. So def train model. Okay. And then activation. We have to pass the activation function. So activation underscore name. Okay. Later on you will find that what I'm telling you. So act, okay, this is correct. So act and act derivative. Okay. So I will write activation so that there is no confusion. So activation derivative underscore derivative equals to get activation functions activation name. Now what we'll do is loss history. Using loss history, we will be able to like plot the graph that how loss was getting computed. So equals to this. Accuracy history also we can do. Okay. Now first thing is that here we have to initialize the weights first. Okay, so whatever matrix we are actually here we are making, we have to create that matrix and initialize the weights. How we can do that? So um, because we are doing this in the form of epochs, like first epoch, second epoch, third epoch, same data. Every time we are doing some computation, we are changing the input. Sorry, we are changing the weights. We are adjusting the weights. So every time we need that matrix should get initialized with same values. Okay. So what we can do is we can set we can set a random seed. So np dot random seed, and we are taking one. So same random number generator will be used. Same types of random values it will generate. Okay. Now, as you already know that there are four things. So there will be, this is W1, this is W2. Here there will be a bias, so B1 and B2. So W1, uh, B1, W2, B2. Okay, so W1 will be there, B1 will be there, W2 is the weight matrix, and B2 will be there. Okay. Okay. So can anybody tell me what should be the dimension of W1? Dimension of W1. 32 cross 1. No. If this is the W matrix, so what is input? 4, and this is output. 4 cross 8. Correct. 4 cross 8. And what should be the dimension of W2? 8 cross 3. Correct. Great. So that is what we are going to do right now. Okay. So W1 is, we will randomly initialize this. So np dot random dot rand n is for normalized. So normalized weights. So np dot random dot rand n. First is input size. So as you already know that we have defined earlier input size. So input size was, actually it was 4. 4. So 4 cross 8 and 8 cross 3. Okay. So this is input size, comma, hidden size. Hidden size. Okay. Then yes, correct. Yes. This is correct code. Now B1 is something we will take zeros, np dot zeros, correct? Yes. So hidden size into output size, and np dot zeros 1 comma output size, correct? So this is what we are doing right now. Okay, I can send the code from cross entropy, correct? So this is cross entropy code. Then this is accuracy code. This we don't need. So I will be deleting this because it will create confusion. Okay. Now, when I will complete this code, then I will share it with you. So I have shared with you this cross entropy and accuracy code. And what about other codes? Softmax I have given. Okay. Yeah. Now we will train the network. Okay. So now this is training loop. So I will write training starts here. Now, for epoch in range epochs. So how many epochs we have taken? 1,000 or 100? I don't know how many number of epochs we have taken. So I have to check. 1,000 epochs we have taken. Okay. Bias, we take zeros generally. Bias is actually a factor that adds, like, sometimes to make sometimes it gets our network gets biased towards training, like one kind of thing it is training. Yes. So to add non-linearity, actually activation functions add non-linearity, Gaurav. So to prevent the model in going to that kind of thing, like same to a particular class, it is biased toward a particular class. We need to, yes. So yes, we have to remove the skewness. Yes, correct. So that is why we use bias term. So np.zeros we take, and it is positive values. You'll get it. So don't worry about bias. Yeah, sometimes if you will not take bias, it is okay, no issues. So now we have to do one thing is, now we have to make those lines clear. So W1 X1 plus B1. So what are the equations? Equations are like this. W1, what we do is we write equations like this. Okay, so W1 into X1 plus B1 will be another W2 into X2 plus B2. Okay. And here we have one more thing to be inserted is activation. So whatever output is, suppose it is Z1. So Z1 equals to W1 X1 plus B1. Then we use activation. So act of Z1 we will take out. So AZ1 will be something, activation of Z1 equals to activation of Z1, and then this AZ1 will be passed here in the form of X2. So AZ1, and then whatever it will be output is Z2. So Z2 is this, and then what we will do is we will make Z2 final output. So output will be softmax of Z2. So this is how we are going to train the neural network in the forward pass. In the forward pass. So this is the equation for forward pass. So let's make some forward pass equation. So Z1 equals to, I'll take capital caps. So Z1 equals to NP dot product we will do. So NP dot and input is X train. X train is the input, and W1 is the weight matrix, plus we have already defined B1. Okay, so this B1 we have already defined. Likewise, what we will do is we will find A1, that is activation of Z1. Then Z2 will be NP dot A1 into W2 plus B2, and A2 is activation of Z2. So I will write it over here. So Z1 equals to W1 into X1 plus B1, and likewise. So you'll be able to do like that. So that this is A1 equals to, suppose ReLU is the activation. So the ReLU Z1, and this is Z2 equals to A1 into W2 plus B2, and this uh, sorry, this this A2 is equals to soft max of Z2. Okay, so these are the equations that we are going to use in forward pass. Okay, now A2 is the output. A2 is the output. So what is the loss? Okay, W2 not W2. Yeah, correct. Caps are there. So make caps only. W1. Correct. Thank you. So Shreen, thank you. Um, so here. Now what is the what is the output? Tell me. What is the output? Output is A2. Correct. Y encoded minus A2. Correct. Loss is Y encoded minus A2. So here Y encoded, not Y encoded, but we have converted those, like splitted those things. So if it is X train, if it is X train, then what should be the output? Y train. Y train. Okay. Yes. So we will use activation as softmax or all that. Okay. Yeah. This is softmax. Softmax. Yes. Correct. So yes. Now, so we compute loss. Loss equals to cross entropy. Cross entropy of what is the output? So what is the desired input output? Y train, comma A2. Okay. This we will loss history. We will append this to loss history. So loss history dot append loss. This means that we are actually storing the loss history. Now, now what remaining? Do we use different activations for Z1 and Z2 as here Z1 and Z2? Z2 for Z2 it will be fixed because it is categorical cross entropy. So we use softmax as loss function. There are multiple classes, so if softmax as loss function. Here we can change depending upon the whatever loss function is doing good because there is no thumb rule. Okay, so now if we have computed loss, now what is remaining? Can anybody tell me what is remaining now? Updating weights. Updating weights. Yes, backward pass. Correct. So we are using now backward pass. So we will write it as forward propagation or forward pass. And this is backward pass. Backward pass. So now we will first find what is the actual error. So we will take it as DZ2. DZ2. Okay. So DZ2 is A2 minus Y train. A2 minus Y train. This is DZ2. Loss dot history. Okay. Whatever loss comes for a particular epoch, suppose there are 1,000 epochs. So for first epoch, what was the loss? So we will take a list. Loss history is a list in which we will keep on like recording those loss values. So append means at 0th position, then first, then two, like linked list we create. So we will have like 1,000 loss values, and then we can plot those 1,000 loss values. So this is something loss history. Okay. Now DZ2 is A2 minus Y train. Now what is DW2? So DW2 will be Z2 into A1 transpose. DW2 will be Z2 DZ2 into A1 transpose because A1 will come this side, so it will be transpose. So what we will do is we will write DW2. DW2 is equals to NP dot dot A1 DZ2. Correct. Okay. DB2 we already know that we need to make take sum. So DB2 is DZ2 x is equals to 0 and keep dimension equal to true. Now we will start with DA1. DA1 is now we are here. Okay. So NP dot dot, because it is A1 is, yeah. So DZ2, because we are taking out A1. So DA1 will be DZ2 into W2T because W2 will come this side. Okay. So DA1 will be equals to NP dot dot DZ2 into W2T. Then DZ1 we will compute. So what is DZ1? Is DA1 into activation derivative of A1, correct? This is correct, suggesting correctly. So we will take activation because ReLU derivative we are taking because we are computing backward propagation. So we have to take the derivative. So DA1, so DZ1 will be DA1 into activation derivative of A1 because ReLU will come this side. So ReLU will come this side. So we will take activation derivative of A1. And likewise, dW1 will be Z1 into X1 transpose. So this one, Z1 here will be Z1 and X train transpose we will take. So X train transpose into dZ1. dB1, as you already know, it is NP dot sum. Okay. So this is how we will compute the backward propagation. Okay. You have to, like, whenever you do backward propagation, you need to like write these equations and then you'll be able to do that. Okay. Now we have got dW1 and dW2. So we will update dW1, dW2, dB1 and dB2. Okay. So update weights. Okay. So Aditya Avasthi says, can I explain it once more? B2. Okay, bias term actually, what we take is we take only the multiplication side of, because we are doing uh, there is no like when we will take a derivative of this in that way it will be zero because it don't have if you know about partial derivatives, so you don't have any term of W2 with this thing, so we don't take derivative of B2 in Z2, like B2 will not take Abdul. So when you'll like read those slides where there is some derivative, so you'll come to know that when loss function is, we take the loss function as a it should be differentiable, and then B2 is not considered because it is not getting multiplied with W2 or weight matrix. That is why. So okay, I'm again telling you. Tell me that what is the output first. So output is, keep this thing in your mind. I'm doing this. What is the output? Output is A2. What is the desired output? Desired output is Y train. Just we take a simple difference between these two, and then we will have DZ2. Okay. This is the first thing that we need this thing. Now, if dZ2 is there, so come to the Z2 term, this term, come to Z2 term. So if dZ2 is there, we need W2. So dW2 is dZ2 into A1 transpose. So dW2 is A1 transpose into dZ2. Okay. Now we need dB2. So dB2 is actually we take the sum of this dZ2. That's it. So don't worry about bias terms. These are actually don't like, you don't have to think about more about these bias terms. Okay. Yes, A1 inverse. If we send A1 other side, we should get A1 inverse instead of transpose. No, we take transpose because we when we are multiplying, I have to tell you then. Suppose uh, because we are back propagating it. So if 3 cross 2 matrix is there, and 2 cross 3 matrix is there. When they are multiplied, it is 3 cross 3. Okay. Now, if 3 cross 2 matrix is there, and we need to like multiply this, uh, uh, how I can tell you, because we are multiplying this this one. I'll tell you. We are multiplying this one with this one. So this is 8 cross 3, and this is 3 cross 8. Now, when we are back propagating, then we have to convert this to this is we have to convert this one as 8 cross 3. So in this way, how I can tell, um, you have to take the transpose of that thing, because this is the reverse way. Like in matrix operations, we do that. 2 cross 3, if we want to multiply, okay, suppose I want to multiply 2. Now this is multiplied with this thing. Okay, we want to multiply this with this. Okay, so we want to multiply 2 cross 3 with 3 cross 2. Will it be same? So you will be able to multiply this? No. So what you have to do is you have to take the transpose of this thing. So when we back propagate, we take transpose of one of them. Yeah. To make multiplication possible. Yeah. So okay. So this we are doing now. Again, DW2 we have taken. Okay. DB2 we have taken. DA1 is Z2 into W2. So Z2 into W2T, and always we have to take the D part of like this DZ2 into W2T. Then we will go to DZ1. So DZ1 is something where we will take DA1, because we have already computed DA1, because this is chain rule. Chain rule means earlier what we have computed, we have to take it into consideration for the next thing during backpropagation. So we are taking where were we? So DA1, we have computed. DZ1 is DA1 into, now we will take the value of A1 A1. Okay. So DZ1 is DA1 into activation derivative of A1. Now, because DA1 we have computed, now we will come back. Sorry, DZ1 we have computed, so we will come back to this thing, and we will compute DW1. So DW1 is DZ1 we have computed. So DW1 is DZ1 into X1 transpose. So X train transpose into DZ1, and then DB1 is like that only. So just keep this thing in your mind that it will start from DZ2, then DW2 and DB2. When these will be there, these will be used after, because this is chain rule, and chain rule says that whatever is computed earlier is now being used for the next multiplication, because we are doing back propagation. Okay, so this is a sort of chain rule written in different lines. If we'll take the same line, then you will be able to multiply directly over here. Okay, so now we have to update the weights. Update weights. This is the thing that we needed actually. So why we were doing this? Because we need to update the weights. So W2 is equals to W2 minus whatever learning rate is there and whatever derivative we have find out. So DW2. Okay. So W2 or capital caps is there. Okay. So W2. W and W2. So W2 is equals to W2 LR into DW2. So likewise, we will take W1 equals to W1 minus learning rate into. So if small is the learning rate, small will be the change in the weight matrix. Okay. So DW1. Likewise, we will do with bias also. So B2 equals to B2 minus, yes, DB2, LR into DB2 and DB1. Yes. Now we will do some predictions. Okay. So we will train the model. So this training will go on with all these epochs. So 1,000 times this will do this the forward propagation and back propagation, and then it will update the weights. Finally, we will have a weight matrix that is adjusted in such a way that we are getting good outputs. Okay. So def we'll do prediction. So predict x. No, we don't want this because we have taken the bias. If bias will not change, then bias is actually something that will be dependent upon the weight matrix. So we'll not change the bias, then what is the use of bias? So we need to change bias. Uh, what is the prediction? So wait, prediction will be um, first we will do A1 activation 1 equals to activation np dot yes x into W1. So whatever input is there, we will multiply it with W1 plus B1. A2 is something we will have softmax of A1 into W2 plus B2 and np dot argmax. What is np dot argmax? Anybody can tell me? Argmax. So argmax is something. Suppose the output comes out to be uh, zero point 0.9, comma 0.1, comma 0.0. So yes, ARG max gives us index. Correct, correct. It returns index. So if there are three classes, so which class? So actually class is index. Index is class, we can say. So if this is the probability that is coming. So at first index, highest probability is there. So first class it is predicting actually. So that is why we used to take np.arg max. Okay. Now we will whatever we have got. So what we will do is y underscore pred equals to, we will call this predict function, predict x. We will call this x function, predict function. Then we will calculate the accuracy. So accuracy equals to accuracy score and y test. So accuracy score is something we will use. Okay, we should use y test and then y pred, because we need to find the accuracy not on the trained data but test data, uh, because we need the data that is not seen by the network. Only after that we will be like we will rely on the network that yes, it is working. So y underscore pred equals to predict. We will do it on the x test and then accuracy will do on y test and y predict. Okay. Now let us check if there is some problem in this code. No. Uh, Now I will copy this code. I have to run this code. Okay. Okay, this is too. I will make a notepad. So I have to delete this. I have to give this file to you all. So you can take this from this file, okay, this code. Now, now the other thing is that now we have to train the model on different activation functions. So activations, we will take a list of activations like what was that? Sigmoid, whatever list we want. So depending upon, but we will take all that. 10H, ReLU and leaky ReLU. 10H, ReLU and leaky ReLU. Okay. So we are creating confusion matrix here to check the accuracy and further on for yes. So you can create your confusion matrix, Aditya. Aditya, you can create by yourself confusion matrix. Okay. Now we have to plot the figure. So plt dot figure. Uh, we'll take figure size and then we will plot the losses on that figure. Okay. So fixed size we will take. Fixed size equals to whatever 12 by 6 or 14 by 6 we'll take. So 12 by 6 and then we will take accuracies. Accuracy is equals to we'll take it in the dictionary. Okay. And then okay. Now for so we have created a figure here and then we will keep on plotting our activations over this figure in this. So for in activations losses comma accuracy equals to uh, we will train the model. So train model over what some activation we are given. So this activation will be pulled out from this particular thing. So this will be sigmoid 10H ReLU every time there will be some activation. So accuracies, because this is a dictionary, so we need to call it like for which activation this is formed. So we will take because there will be dictionary. Do you know dictionary value pair? Okay, train model. Okay, we have not returned anything. Okay, yeah, correct. So we have not returned anything from train model. So return, what we have to return is uh, loss history. So return, we will return loss history and accuracy. So there will be one accuracy we are taking. Okay. Accuracy for like accuracy history we don't need history because we are not computing accuracy in each epoch. In each epoch we are not computing accuracy. If we are computing accuracy in each epoch, then only we will make accuracy history. Right now, for a particular input we are getting some accuracy for all for after getting that model trained, will have an accuracy score for each sample in X test. So that is why. And we will take it, we will do this by taking mean and all that. So we'll take the accuracy score as mean. So there will be one value of accuracy. Okay. So accuracy is where were we? Act equals to ACCs. Now we have to, because ACC is this, so we will take accuracy and then we have to plot. So PLT dot plot. We have to plot losses, and we have to give the label. So formatting we'll do some formatting on that label. So F act, and what is the formatting? F act. And the formatting is we have to give parentheses, and we will close this, and then we will give formatting as ACC equals to um, when do two decimal places. Okay, so ACC dot 2F, two decimal places. Now this is done. We will come outside the for function. Xtrain is not defined. So okay, losses. Xtrain. Okay, this cell we didn't run. So this cell we have to run. So whatever, yeah. So losses is something x is equals to 1, np dot mean argmax y true x is equals to 1, np dot argmax. X is 1 is out of bounds for x. Okay, let us check. Accuracy score. np dot mean y true and y pred. np dot mean np dot argmax y true x is equals to 1. Correct? It is correct. Equals to np dot argmax y pred comma x is equal to 1. It is correct. So what we can do is losses comma accuracy. Streams. Whenever we do is it is like that. Spread. Is it printing something? No. What is the problem? Y true and Y pred, no? So sorry. Y underscore true is not defined. Test. Thirty comma 3. Okay. So it is 30 only. Why it is 30? Why pred is 30 only? Why? Output underscore size equals to 3. Then to Z2. Y train A2. Hmm. Okay. So what we were doing, we have to return A2 over here. Now I will do this like yes. Now what we will do is we will plot. Okay. Do plotting. So no, this is not required. Okay. So there will be plots and then we will do some thing. Okay. So plt dot title. Uh, so we'll write plt dot title is this is our so this is loss curve for MLP 3 class. What is this? We have made for iris dataset. Yes. So X label is epoch, correct? Y label is loss. Okay. Let us check. So it is not giving T dot Y label. Epoch's loss. PLT dot plot losses. But it should plot. So I think losses. So we have to check with losses also. So this is correct. Uh, return loss. So loss history. So return loss history. Okay. So we will find it out. So what is train model losses? Okay. So print uh, losses losses dot shape. Okay, len losses. So we will take len losses. So loss actually it is for epoch and range epochs. Yes. Hmm. Okay. Yes. So there was some problem with the alignment, like what we can say. Yeah. So we have got the losses, and here you can see that suddenly loss is going down with ReLU consistently, but loss is very less when we are comparing with it with 10H. So here 10H is performing very nice. Okay. So 10H and as well as sigmoid also. No, no. Yeah. So I think I will share this code with you all, and please let me know what if there are any questions. Otherwise, we will close this session today because it is all from my side. Anybody who wants to ask a question? You have some question?
Anybody who has questions, please drop in the chat.
Out of all activation functions, so here you can see that the function that has not that is not giving so much variation while it is getting trained, and the loss is very small where we are reaching very small loss after epoch. So we can check here over that the this orange line and blue line are doing good, so 10H and sigmoid are doing good.
Sir, I
Learning rate, okay. Can you change the scale? Scale change, what scale change? I don't know. What, like we can change the figure size. We can change because we are having 1,000 losses, so we can add more losses by training it for like 1,000, 4,000 or 3,000 epochs. We can check likewise. So whatever loss value is there, it will automatically take that range of loss, because whatever loss comes from these, it will automatically take and then it will plot. So depending upon that, every line seems to be correct, but I am not getting any output. What can okay? So VN Lakshman, Mr. VN Lakshman, I will send you the code. I will leave this code with you all, and then you can check it by your own. Okay. By this evening, I will share it with you. Somebody asked me that why learning rate is used. Learning rate is something where you need to change the uh, or you have found the gradient, and then how much change you want, like so how much change is defined by the learning rate. Like there is some change, but how much, how if learning rate is very small, there will be very small change in the weights. So sometimes what happens is we take the large learning rate in initial epochs, then we will lower down the learning rate. So it is known as um, LR reducing, learning rate reducing, learning rate tuning, and all that. So that is why. Do increasing epoch will, yes, sometimes this is, see, this is very small problem. So increasing, because we are reaching very small loss value, it is nearly zero. So if we'll increase the number of epochs, it will not affect that much. But if you are taking a good problem where the loss is very high, then you can increase the number of epochs. You can change the learning rate and all that. So that is why. So leaky ReLU is here. You can see that sigmoid is giving one accuracy as 1, 10H is giving 0.97. It means that there is more loss in 10H. Yes, yes, yes. We can have some test cases like you can take any input of dimension 4, you can convert that input, expand that input, and then you can test that input. Okay. So I have another session right now. So I need to leave right now. In the next session, we can discuss more. Okay. Testing is done now. Testing we have done. See here we are using X test. If you want to, like, suppose it is, uh, let us take some vector v equals to some inputs we will take. So suppose I am taking this input. So what you have to do is you have to now if you will take this input, you have to convert it in this using this standard scaler. So you can take an input. Now you have to convert this input using take this as your take home assignment. Okay. So what you have to do is take one input, apply standard scaler. Then what you have to do is now you have to apply. You have to expand the dimensions. Dimensions expansion means since this is 1 cross 4, 1 cross 4. So you have to make it like 1 cross 4. Okay, like this. So then you can predict this expanded. Then you will get some arguments, like you will get uh, after prediction we are getting softmax. So you will get a vector with 3 values. Then what you have to do is find arg max, and then you will get the class. So whatever class it is, 0, 1, or 2. Okay. So you will find which class is 0. Okay. So this is your exercise. You can do it. I have given you the steps how you can do that. It's very simple. Okay. Thank you all uh, for having so much patience and listening to each and every step in this particular session.
Thank you,
So
sir,
yeah,
for
thank you.
joining us today and for such a detailed session. Your clear explanations and insights are truly valuable and greatly appreciated by all of us. Thank you so
Thank you.
much.
Thank you so much. Thank you. Thank you. Thank you. So okay, so I'll be sharing the code file, and you can, or I'll share it over here only. So please wait for a minute or so. So this is summer school session 3. So this is So I'm sharing this file to everybody. Uh, okay, chat. It is not allowing me to share, but
Okay.
because recording has been stopped or something has. Okay, okay. Now I will do that. So your computer. Now I've got the access. This thing. Uh, Downloads. Yeah, send. Okay, so I've shared this file. You can so you can take this Canvas teaching platform. Okay,
Sir,
so Canvas.
sir, I
I'm
can
not.
directly
Mhm.
contact you over texting or on email. Sir,
Okay,
you can share me over there. I'll just text you.
okay. Sure.
Okay, and I'll then directly share it with the students and participants.
Sure.
Okay, thank you so much, sir.
Yeah. So you people will get this file. I'm sorry that I have attached to this to Bakshish Sachar. So, one Sunana, 1 minute. Let them take this file. Oh, it will not take no more than 1 minute. Okay. So I've sent this file to everyone. Please download it. Sunana will close this session within a minute. So please download this file, and I will share another file with her that is neatly created. So you can take that file also. All right. Thank you. Sunana, you can close this session after 15-20 seconds or so.
Yes,
Yeah.
yes, yes.
Yeah.
Sir.
Yeah.
Thank you so much, sir.
Thank you so much. Thank you. Thank you, everyone.